So hello everybody, thank you for joining us and welcome to the final ASTRO 3D ECR Astronomers in Australia seminar series. So my name is Dr. Amelia Fraser-McKelvey. I'm a postdoc at the University of Western Australia as part of the International Centre for Radio Astronomy Research. So before we begin today, it's important for us to acknowledge the traditional owners of the land on which we meet. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build today. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. Myself and our first speaker are speaking with you today from the land of the Whadjuk Noongar people, and our second speaker will be presenting to you from the land of the Djibouti and Djirwara people of the Toowoomba area. We pay our respects to their elders past and present and extend this respect to all First Peoples joining us here today. So why are we here? So the series is facilitated by ASTRO 3D, which is the ARC Centre of Excellence for all sky astrophysics in 3 dimensions. So COVID-19 has affected our ability to travel and present at international seminars this year, especially for us in Australia. The time zones often mean that meetings take place at 2 or 3 a.m. in the morning. This lack of opportunity to network could disadvantage our junior astronomers when entering the job market. And so the series aims to combat these issues by providing a platform for junior Australian astronomers to present their work to the world. So we've got 2 talks for you today over this hour. They're both going to be 20 minutes in length with 5 minutes for questions. And please, I could ask you to save your questions for the end of the talk. You can either raise your hand or pop them in the chat function. We are also recording these talks and we're going to put them on the ASTRO 3D YouTube channel. So by being here today, you're agreeing to abide by ASTRO 3D's meeting code of conduct. Okay. Our second speaker is Alexis Heitzmann from the University of Southern Queensland. And Alexis is speaking on how can we find big baby planets around young active stars. So Alexis, you can go ahead and share your screen when you're ready.
All right, so hello, I'm Alexis Heitzmann. So I'm a third year PhD student at the University of Southern Queensland. And today I'm going to talk about a very recent and very cool finding about the obliquity of the youngest transiting hot Jupiter. So in this talk, I'm going to talk about exoplanets. So exoplanets are all the planets that are outside our solar system. We have found more than 4,000 of them now, for now 25 years, 30 actually, almost. And so there are many techniques to discover exoplanets, and here I'm going to focus only on one, which is the most successful, and it's called the transit method. So on the right hand side of this slide, you can see an animation. So when you have proper alignment and a planet orbiting a star, and it just happens that the planet crosses the line of sight between you and the star, then when it eclipses, the star is going to create a dip in the light curve that you can see on the bottom. And this allows us to recover the size of that planet. And if we find many successful transit, we can also know the period of the planet orbiting the star. So on the left, you can see all the planets that we found this way. The x-axis is the period, and as the planets are closer, they are hotter because they are closer from the star and they get more light and insolation. And the y-axis is the radius. The type of exoplanets I am interested in are what we call hot Jupiters. So these hot Jupiters are within the circle here. So they are hot, very close, orbiting very close to their star, and also they are Jupiter-sized planet. We think that roughly 1% of Sun-like stars host this hot Jupiter, but as you can see in the graph, they represent quite a significant fraction as from what we found. And that's because of observational biases. Because they are large and close, they are more likely to yield detectable transits. But these planets, so they were the first that was found was 51 Peg-b, a hot Jupiter, but they are really mysterious because we still don't understand how they form and how they even exist. There is no such planet in the solar system, and it's still a mystery. So we have many theories. The first one is to explain why they exist and how they form. The first one is in situ formation. So in this scenario, the hot Jupiter forms already directly next to the star. But this is a bit hard to explain from our understanding because we don't think there is enough material in the vicinity of the star when the protoplanetary disk, so that's the disk that's going to form the planet that's around the star, we don't think there is enough material to create hot Jupiter. So the mainstream theory is called migration. So in the migration scenario, the Jupiter-sized planet is formed far away in the disk and then migrates inward. And so that can happen because of interaction between the planet and the disk itself. So the disk is made of gas and dust, and gravitational interaction between the two can shrink the planet orbit. Or it can be different mechanisms called high eccentricity. So other planet in the system will, again, the Jupiter forms far away, and then its orbit is going to be excited by other planets nearby and become very eccentric. And then the tidal forces that the star exerts on the planet when it's really close will circularize the orbit. And so in the end, you end up with a very close and hot Jupiter. So to find out which scenarios and what proportion of each scenarios are true and are actually happening, we have different pathways we can explore. And so here I'm going to talk about two. The first one is age, and the second one is obliquity. So age is quite straightforward because we expect in situ formation and disk migration to happen before by definition, to happen before the disk has vanished. Because after a few tens of millions of years, the disk is going to disappear, and then only can high eccentricity type migration happen. High eccentricity migration can happen during a very long, different time scale, but we expect most of the planets formed this way to arrive early. So the key is to study very young stars, because very young stars are going to tell us, are going to help us discriminate between those two. There is a bit of a shady area between 10 and 100 million years. But if we give enough statistics and an occurrence rate of how many Jupiters are there around young stars and mature stars, then we can find out the mechanisms. The second way we can try to discriminate between those formation channels is obliquity. So basically, obliquity is the angle between stellar spin axis and the planet's orbital period axis. What we actually measure is called the sky projected obliquity, because of course the star is projected on the celestial sphere. But as a proxy, we can say that sky projected obliquity less than 20 degrees is an aligned system, and if it's more than 20 degrees, it's a misaligned system. So how can the knowledge of that obliquity help us to discriminate again between formation channels? So this time, again, this migration and in situ formation are rather smooth scenario. We don't expect them to send the planet's orbit very violently, and therefore we don't expect it to tilt the orbit of the planet. And therefore, if the orbits are aligned from the beginning, then they should remain aligned. However, high eccentricity is very much more violent and can lead to much broader range of obliquities. And so if we find that systems are more aligned, then we can expect that they were probably formed by disk migration or in situ formation. So there is a few caveats to that. It's not that easy to disentangle, because first, as I said before, we measured the sky projected obliquity, and we need to compensate for that. And also we know that star can actually be realigned by the planet. So the planet can have also tidal forces influencing the star and realigning both, yielding a line system, which means that a primordial misalignment would be erased. But if we look at very young star, we are fine, because this would not have time to happen, because this takes quite some time. And also another caveat is if the disks are primordially tilted. This can be because of binary star systems, for example. And also some theory says that the stellar internal movement can also act to shift the inclination of the stellar spin axis. So we've been focusing on measuring the obliquity for young systems, and it's been going better and better in the recent years, and especially in the last 2 years. As you can see, we are starting to get really young measurements thanks to tests. So it's not always easy to measure the age of stars, but when we do, and we can get the obliquities, this is great to start in discriminating these mechanisms. In white, you can see the ones that have been found by TESS. So TESS is the Transiting Exoplanet Survey Satellite, which I'll just explain a bit more afterwards. But what you can see here is that in the last 2 years, we found really young planets. And today I'm going to talk about a new one we found, like a new obliquity we measured for a system even younger than those. But first, let's just present TESS. So TESS is a space satellite that's been launched in July 2018. And this video is showing you how it works. So it scans the part of the sky and stay 1 month in each, and try to look for variation in the brightness of stars, so to detect the transits I explained in the first slide. It's been starting in the southern hemisphere, then it's been back to the northern, now back to the southern hemisphere, and at the end of this year, it's going to turn back to the northern hemisphere and also observe the ecliptic, because you can see here on the ecliptic plane here, there is a big gap. So we're going to get a lot of new candidates for new exoplanets. So as I said before, we measured the obliquity of the youngest transiting Jupiter, which is HIP 67522b. So this star is extremely young. It's 17 million years of age. The planet has a size of 10 Earth radii, and the mass is to be confirmed, but it's less than 5 Jupiter mass, and it orbits very close to the host star. And so we got a transit of it on the 14th of May 2021. So now I'll explain how do we measure actually the obliquity, and then I'll go on and say what did we find for this particular system. So to know the obliquity of a system, we need to catch a transit, as I showed, except not in photometry, which is you just measure the intensity of light coming, but in spectroscopy. So we use the SMART's 1.5 meter telescope that feeds its light to Chiron, which is the spectrograph. And so that spectrograph is going to decompose the light into its wavelength component. And so you get a stellar spectrum. So this stellar spectrum, you can see here the lines, the absorption lines from the spectrum. And what we do is that we do a weighted sum of all of this line, and we get an end product, which we call the line profile or mean line profile. So it's reversed, but basically this is a weighted sum of what's on the right. And this tool is going to help us to look at variation in brightness on the star. So let me show you an animation. So what happens here? We have a planet transiting a star, and the blue and red are showing the Doppler effect. So as the star rotates, one hemisphere is going to come toward us, and that light is going to be blue shifted, and the other hemisphere is going to be red shifted, which means that as the planet transits, it's going to occult light at different velocities, and the net, it's going to create a net imbalance. And you can actually see in the profile the planet going across the stellar disk. In the case of a misaligned orbit, then the signature is going to be different. And with that, we can recover the obliquity. Now, this is good for mature stars, but for really young stars, it's a little bit more annoying, because really young stars are really wild. They get strong magnetic field and mainly stellar spots. And these stellar spots, because they have a different brightness, will also impact the shape of our line profile. So you can see the same animations, but with the spot crossing, and you can see the variation of the line is largely affected. So to model this, so you can see the animation before is our numerical model. And this is the blue curve you see on the top right. And our data on the left is the line profiles that we got from the star during the transit. And so we're going to fit those. So we're going to try many different configurations using an optimization algorithm of the simulation you saw before, and then come up with our model, and then just see how well our model fit. We also fit the photometry at the same time. The test photometry, so looking at the variation of brightness of the star, we did both simultaneously using Dynasty, which is a nested sampling algorithm. equivalent to a MCMC. Maybe that's we can talk to more of you. And so by this we can get all the parameters of the previous animation. So the obliquity, the size of the spot and its position, and from the photometry we can recover the length of the transit and the size of the planet and so on. So for the results, so this plot is showing the results. So basically what you see here is, so on the right you have each of our line profile for the observations, and time goes upward. And on the left image, each line is the variation relative to a mean profile from each of the epoch. So what the left shows is basically the variation of the surface brightness of the star. Time goes upward again. The vertical line are the rotation speed of the star, so the V sin I, and the two horizontal lines are the beginning and the end of the transit. So the animation I showed you before with the spot going on, if we use this animation to get the same plot, this is what we get on the middle. And once we subtract our spot model to the data, we have the residuals on the bottom. And so if we look closely at these residuals, we can see two main features. The first one here is another spot that we didn't model because it didn't get in our way to know the actual obliquity of the planet, which is the second thing you can see on this plot here. This is the planet transit. And this tells us that this planet is perfectly aligned. What you can see on the right is, again, the animation you saw previously, with the spot being the middle left plot and the planet being the D panel, the right panel. And so in the end, what we find is that this planet is aligned and this system is aligned. And that's very interesting because for the first time for a hot Jupiter, we can actually be quite sure that high eccentric migration was not what happened for this system. So of course it is a single system, and to make sense of all it with statistics, but we can say that this hot Jupiter came to life through this migration or in situ formation.
5 minutes left, Alexis.
Thank you. So this plot is showing the systems for which we know the age, because again, the age is not always easy to get, and for which we have measured the obliquity. So we have in yellow the smaller Neptune-sized planet, and in blue the larger Jupiter-sized planet. And what we can see is the clear cutoff at 100 million years. Of course, it's very early in the days of finding obliquities for young systems, but we can clearly start to see a trend here, which is systems with more than older than 100 million years have a much broader, are much more distributed along the obliquity axis. And systems that are younger seems to be all aligned. So the takeaway here is that HIP 67522 spin axis and the orbit of its planet are well aligned. And as I showed, this is the youngest transiting gas giant that we have with a known obliquity. And this planet, therefore, we think was from either in situ or via this migration. We also saw in the last plot that there is no apparent misalignment for planets less than 100 million years old. And so it's going to be very interesting now, because as I said, TESS is going to turn to the ecliptic, and we're going to have much more young planet candidates. And this is going to open the way to much more obliquity measurements. And with this, we can hope to finally get a better grasp of the different mechanisms and the proportion at which they occur for this very, very strange planet. We can ask then, if we see this trend continuing of young planet being aligned, we can ask, when does that cutoff happen between aligned and misaligned orbit? We can also ask the question, does it mean that we see different formation channel at play? It seems that broader obliquities, broad distributions of obliquities mean high eccentricity mechanisms. So if we see, we can try to catch hot Jupiter very eccentric, that would mean that they're actually experiencing this migration scenario. If they are formed in situ, it will bring a lot of new constraint on disk properties, because so far we thought it wasn't really possible. If they are formed via disk migration, then what are the timescale of this migration, right? How fast does it happen? And finally, are most of the disk like we are seeing primordially aligned, and if yes, why? So this discovery is going to bring a lot of new questions, and there are going to be in the next year at least 4 new planets that are currently being measured. And yeah, so I'll be happy to take any questions you have for that. Thank you.
Thank you very much. Great talk. Great talk. We've already got a question in the chat, so I'm going to ask that one first. It's from Daryl McQueen. Daryl asks, can migration still happen after the disk has dissipated? What I'm wondering is, can the NICE model mechanisms explain hot Jupiters, or is there a limit to those effects?
Okay, so the 3 categories are broad categories, but for migration, disk migration, it needs to be happen when a disk is here, because the migration is driven by interaction between the planet and the gas, basically. And the high eccentricity migration, on the other hand, cannot happen between this phase, because if you want to excite a planet to a very eccentric orbit, then the gas will in the disk will act as a damper of angular momentum change, and therefore the only way is to have a circular, smoother migration. I hope that answers the question.
Okay, thanks. Let's go to Simon Murphy. Simon?
Hi. As you said, a caveat of all of this is that disks can have primordial tilts. So aside from the fact that your results show that young planets are typically aligned with their host stars, have primordial disk tilts been quantified in any way?
That's a great question. No, but I think it's okay. So if we would have a lot of primordial misalignment, I think we would see it as misaligned planet, and it would be actually a question: what is happening? Is it a misalignment due to a scenario, or are the disk actually misaligned primordially? Now we seem to see that they are aligned because we see a line system.
Yeah.
Thanks, Simon. We got any further questions? Check.
I can go again if no one has any.
Sure.
Hypothetically, if a disk were tilted, would you expect the planets to have an intermediate obliquity, so somewhere between the plane of the disk and the plane of the stellar rotation, or would you expect them to be firmly embedded in the disk?
So do you mean that the disk and okay, so the misalignment means the axis of the star is not aligned with the disk, but the planet is still embedded in the disk, if that makes sense.
Okay, so the planet has the
I don't
same
think we could
alignment.
expect that's a good question, but I don't think we could expect a planet to be misaligned with the disk it was formed in, if that makes sense. Or maybe after like strange mechanism, but no, I don't think that's yeah.
Thanks. Any further questions for Alexis? If not, then I suggest we leave it there. Let's thank Alexis again for a fantastic talk.